Hello ERA users. This video will walk you through how to use the MEMlog feature in the Earth Builder, which we recently released. If you're watching this video later in time, this feature came out mid-April 2018. To access the MEMlog, and I've created an example here where we already have some drilling data to overlay for comparative purposes, but if we want to access the MEMlog, we can do so over here in the Earth Builder. And the only inputs that I've put in so far are just some basic information. Formation tops in the Geology tab. You notice across the top, we've now got tabs Geology, Temperature, Logs, and Rock Properties. I've input the formation tops. I have made sure that my geothermal temperature profile is correct. And then the next tab is Logs. So before we can generate a mechanical earth model from logs, we need to put the logs in. And you should see a screen that looks something similar to this. And what I've done off screen here, I'll just pull it over. I've got an Excel spreadsheet where I've extracted the log channels that I want to input. In future versions, you'll be able to just import a LAS file and identify which channels it is that you want to bring into ERA. But for now, I've just done this outboard in Excel. But you just select the channels that you want, and the most important ones, in order to do this, we need gamma ray, bulk density, and your compressional and shear acoustic travel time, so DTC and DTS from Quad Combo. So if I haven't mentioned it before, Quad Combo is kind of the bare minimum needed in order to do this work, and preferably with dipole sonic tools. So I've copied, and now I'm just going to Control V into my table here. Always make sure that the units that you've got in ERA are the same units that are used in the log. You can either modify the units outboard in Excel, or you can select one of the units that we already have preloaded in ERA. Now you'll notice all the log channels appear now. I've got them all displayed in the order that I want. You can adjust decimation as you wish. Decimation will just clean up the logs rather than having them be so quote unquote spiky. You can run an average across whatever interval you choose. Of course, if you get too coarse of an interval, then ERA doesn't like that and says, let's not do something totally crazy. I tried to type in, I guess, less than 0.5, but at 20 feet, we're starting to lose a bit of resolution. 5 feet is kind of a reasonable point where you still have some character to the logs, but it's not totally spiky. Next step in the process is to move over to rock properties, and rock properties is where we can decide whether or not we're going to build a pure mechanical earth model. Somebody else has done the work for us, or we're going to build a mechanical earth model from logs, MEMlog, or we're going to go the traditional equivalent mud weight route where we just put in pore pressure, frac gradient, collapse pressure versus depth. This point of all this exercise is to do the MEMlog. So when I choose MEMlog, it will introduce a 6-step process. So these 6 tabs are what we're going to work through in sequential order to build ourselves an earth model. And the first tab is QC, and what that gives the user the opportunity to do is quality control the logs, make sure that any bad data in the log measurements is thrown out and not used to calculate any of our rock properties. You can see what kind of rules are used. You can even turn off those filtering rules if you want. You'll notice that there's a caliper measurement here that's totally bonkers. Here I threw that out, said I don't want to use that. But when you turn that on, you can adjust what the rule sets are with the advanced button. And it just kind of goes through each one of the channels and says, okay, what do you consider to be absurd values? I know if my hole is washed out to more than 20% of the hole size, that's probably not going to give me good density readings. It's probably not going to give me good sonic readings, even though most of those logs are compensated for borehole dimensions. There is a limit to how effective the compensation routines can be. So by default, we say 20%. Crazy values for bulk density, crazy values for gamma ray, crazy values for your compressional slowness. All those values will just be ignored. Default settings should be good in most cases, but you have the ability to adjust that if need be. Next step in the process is to move over to lithology. So in the lithology chat tab, what we want to do is distinguish shales from sands. And the first step is to identify the shale baseline. And you can either do that by adjusting this value manually, typing in 90 there, for example. And what you'll notice is over here on the gamma ray log, the shale baseline, which is the line to the right, You can also grab this with your mouse and move it left and right. That determines anything to the right of that line we'll consider a shale, and certain equations will be applied to shales. Or to the left of the line, it's considered not shale. And it's 100% not shale to the left of this other line, which is what we call our sandstone baseline, although it's maybe not a totally accurate term. We should just call it not shale baseline, and that's where we define our clean formation. So you could take it to the extreme and say, okay, only extremely clean gamma ray intervals are what we would call clean sands or clean carbonates, clean salts. But what I usually do is adjust that sandstone baseline to be about 10 values less than my shale baseline. And I'm just going to start with a shale baseline somewhere in the neighborhood of 86, 87. That looks about right. I know most of these formations over here are pretty clean shales. So that's what I'll go with. And for my sandstone baseline, we'll move that, yeah, say maybe about 75, 76 or so. Keep it pretty close to my shales. And you'll notice over on the left, the stratigraphic column will be color coded. Anything that's a clean sand, it'll have this yellow with little specks in it. And if it's a clean shale, it'll be gray with dashes. If it's a dirty shale, if it's got a little bit of sand in it, then it'll be brown, indicating, say, a siltstone or something that isn't totally clean, mudstone, high gamma shales. Now, the other sequence or workflow that we need to go through here is to identify the exceptions. And the two exceptional lithologies are carbonates and salts. I don't have any salts in this example. This is in this area that we're in South Texas. But I do have some carbonates. The Austin chalk is this formation down here, and I also have the Buddha limestone. This is the very last formation that was drilled. If I click Add Carbonate, what I can do now is click on the plot and identify the region where carbonates appear. And I know that anything that is low gamma in this region is going to be considered the Austin chalk. And I know down here below the Eagleford, I've got another zone, which is the Buddha lime. And so I can just click on those intervals. It doesn't have to be perfect because all ERA is doing is just looking for any zones that are below my sandstone baseline. And in that interval, it will treat that as a carbonate rather than as a sandstone. The reason why we have to do that is different correlations are used to calculate the unconfined compressive strength when we're in carbonates than when we're in sands. Likewise for salts. So these are just kind of identifying the exceptions, things that are not sands. Okay, I'm through with my lithology process. Now I'm going to move on to overburden. And overburden is probably the simplest aspect of building the mechanical earth model. The default scenario is auto gradient. We can also do integrate density. And integrate density will use your bulk density data. Anywhere where you don't have bulk density data, it will use kind of some standard equations for calculating the overburden. And you can manipulate the coefficients in those equations by clicking on this advanced button. So there's a coefficient and an exponent. It's a power law equation. You can adjust those numbers. I wouldn't mess with those numbers unless you really know the area that you're working in. The default settings are pretty good and close enough in most circumstances. So integrate density would be the option that you would choose if you have bulk density. Now we'll move on to pore pressure. Now, by default, ERA will assume that you've got a normal pressured basin, and that's what uniform gradient means. When you click on a uniform gradient, you can define what the normal hydrostatic value is in your basin. But in this case, I'm working in an area of overpressure, and I want to use my sonic logs to calculate pore pressure. So I'm going to select sonic correlation. And when I select sonic correlation, you'll notice over here that two red dots appear, and I've also got this golden curve. And if I left click on my mouse, I can move these two control points. And what I'm trying to do is establish what the normal compaction trend line is, what the acoustic velocity ought to be in this area if I had normal compaction, if overpressure was not the consequence of undercompaction. And so when I click on these dots, I can manipulate the curve, and that will take some trial and error and a little bit of knowledge in your area. But what I'm finding now is I've got pretty normal pressure down to about 7,000 feet, and then the acoustic velocity starts to deviate from the trend line, and I'm getting into an interval of overpressure. If you have pressure measurements anywhere throughout the overburden, one of the calibration factors is this Eaton exponent, and you may want to adjust that number up. You will amplify the intensity of the amount of overpressure that you calculate by adjusting that value. And ERA will warn you if you're starting to put in numbers that are a bit unrealistic. And by default, 1.3. Let's just go with that and see how that looks when I generate my Earth model. How those values are being calculated is using a smooth acoustic velocity, and you can adjust the smoothing interval with this advanced button. Over here, you notice the smoothing interval by default is every 100 feet. So we average the shale velocity. So those zones that are considered clean shales, we're going to average the velocity at moving average every 100 feet. And that's how we arrive with this red curve, which is used then to calculate my pore pressure. Now, if I were to go to higher resolution, a smaller smoothing interval, you'll notice you get more character in the curve. And that's probably a bit unrealistic because over millions of years, we're going to reach equilibrium pressure through most of these zones. So I'll leave it at 100 feet. Once I feel like I've got my pore pressure pretty well dialed in, I can move on to horizontal stress. And you'll notice that horizontal stress, there are two drop-down options of how we'll calculate that. I can either calculate my minimum horizontal stress from the vertical stress, my overburden, or I can use the overburden gradient and Poisson's ratio. And if you have dipole-sonic, I would advocate using Poisson's ratio because each of the formations that you drill through are going to have varying levels of stiffness, and stiffness will impact how much stress gets translated from the vertical direction to the horizontal direction. And then you can calibrate what we come up with there with this number. If you had a leak-off test, for example, I happen to know that in this area we did a defit, and the defit came out to about 15.1 pound per gallon down here in this clean chalk, and that required a calibration parameter of, what was it, about 1.7 in order to mimic what was observed in the offset. So having that sort of either leak-off test in this subject well or in an offset well, or defect closure pressure will allow you to really dial in that horizontal stress. And then the other input here is your maximum horizontal stress, which is just simply treated as a ratio of effective maximum horizontal stress divided by your effective minimum horizontal stress. Calibration is our last option here, and what you'll notice is now I've got the full output for this specific log. I'll have pore pressure, my losses gradient, and my breakdown gradient and overburden all overlaid here. And ideally, what you would start to do is overlay your drilling ECD or your swab loads or a kick that you may have taken, or any means of information that you have to dial in the accuracy of the model. This is where you could manipulate that with either failure criterion or a stability factor, where you can kind of artificially boost the compressive strength, which will adjust the output. Those are all just kind of the last little knobs and switches that you have to dial in your model. Once the MEM is built, now you also have the ability to change your well path, and these limit curves will be altered based on your trajectory. And you can also interrogate the overburden and build inclination versus mud weight plots, azimuth versus mud weight, see which formations are really sensitive to inclination and azimuth, see which formations are not so sensitive to inclination and azimuth. You can also generate a rose plot, show what inclination and azimuth in any direction or inclination combination look like for a specific zone. So that all is very useful output of the model. And now when I'm back at my main geology page, I'll also see the output of the new MEMlog that I've created. Of course, you can always create the plots in a form that is useful for a report. Just by double clicking. You can change your scales, change your depth range. You got something that you can export to a file. The other thing that I will point out is once you've built your MEMlog, when you're down here and I've got a well with actual drilling data in it, if you were to pull up your, or maybe I don't have drilling data in this one. If you were to pull up like a mechanical specific energy plot, you could overlay your confined compressive strength. And unfortunately, I thought this example had that data in it. It doesn't. But you'll have your confined compressive strength now, and you can overlay your drilling MSE on top of confined compressive strength that was afforded to you by having the MEMlog built. So a lot of useful stuff there, and this video will evolve as we add more features from within MEMlog. If you have any questions, you can always email KMT support at kmtechnology.com.